So now let us start with the uh, DTL logic family. So we have seen last lecture about RTL logic family. Okay, now today we are going to deal with the DTL logic family. In DTL logic family, as you can see over here, there are diode as well as transistor. Okay, so this is diodes in the input side. Okay, this is the transistor. Okay, so this transistor will be on whenever you are applying the high voltage, whenever you are applying the high voltage in the input side between base and ground, you can say. Over here, whenever we are applying the high, then the transistor will be on. Now, whenever the transistor is on, okay, what we say, there is a short circuit between collector and emitter. There will be almost 0 volt between collector and emitter, and your output will be 0 at that time. Okay, now whenever we will apply low over here in the input of the transistor, the output will be high, that is VCC will be the output, so we will say it as logic 1. Okay, now let us try to understand this DTL logic family. Now if you are seeing this diode D1 and D2 over here, so when this D1 will be on, you can see one anode of the D1 is connected with the VCC. Okay, same way D2 is also connected with the VCC. Okay, and A is the input 1, B is the another input. Okay, so when this D1 will be forward bias, whenever I am applying 0 volt, that means whenever I am applying ground over here, 0 volt, it will be, D1 will be on. Same way, whenever I am applying 0 over here, D2 will be on. Okay, now what happens when you will apply 1 to the A? 1, that means VCC, 1 that means VCC. So what will happen to the diode D1 at that time? Over here also it is VCC, over here also it is VCC. So this will be open circuit whenever I am applying 1 over here. Same way in the input B also, whenever I apply 1, what will happen to the D2? D2 will be open circuited whenever I am applying 1. Okay, so now friends, you have understood that when D1 will be on and D2 will be on, and when the transistor will be on. Okay, now we have to understand that how this will be operated. Okay, so let us start analyzing for the first combination. Whenever my inputs are 0 0. Okay, whenever my inputs are 0 0, I have to uh, analyze this circuit, and I have to find that when this circuit will be on. Okay, so whenever this A is 0 and B is 0, first combination, both are 0 0. Okay, A is 0 and B is 0. Okay, say this is B. Okay, so and my what is my output? I want to find Y. Okay, this is my output Y. Okay, so whenever A is 0, B is 0, what will happen over here? The diode D1 will be forward bias, so all this VCC will be grounded through A or B, both are 0 right now. Okay, so what will happen? This D3 and D4, they will remain open because the VCC is grounded through this path or this path. So D3 and D4, they will be open circuited, so there will not be any enough voltage on the transistor. Okay, on the input of the transistor, so input of the transistor is applied with the low, okay, low voltage, or you can say 0 volt over here. Okay, so the transistor, whenever I'm applying 0, it will be going to give me output VCC, that is 1. So whenever A is 0 and B is 0, my output is 1. Friends, same theory will be repeated, either this is 0 or this is 0. Okay, so let's say another combination, A is 0, B is 1. Okay, so if A is 0, all this VCC will be grounded through this path. So again, see, although this B is 1, this is open circuit, but both of them are in parallel. So either एक path parallel का ये short circuit होता है, भले ना ये open circuit रहा, all this VCC will be grounded through this path. Okay, so what will happen to D3, D4? Again, they will be open circuited. There will not be any you can say voltage applied on the transistor, again it is 0 volt applied, the output will be 1. Okay. Next, okay, this A is 1 and B is 0. A is 1, that means D1 will be open circuited, but B is 0, so D2 will be shorted. So all the VCC will be passing through this D2, and you will have all the VCC grounded through this. So D3 and D4 again they will be open circuit. Again transistor will be applied with a 0 volt, so the output will be VCC, and if the output is VCC, we will say the output is Y is equals to 1. Now the important combination, when both the inputs are 1, 1. Both the inputs are 1. Okay. So when A is 1 and B is 1, so what will happen? When A is 1 and B is 1, A is 1, B is 1, D1 is also open, D2 is open. Okay, so then now there is no path for the VCC to ground it through any of the inputs. So what will happen? VCC will come this way. Okay, and D3, D4 they will be you can say forward bias, and the VCC will be applied between this base terminal and the ground, you can say. So high is applied on the transistor input. If we are applying high, that means 1 will be getting 0 volt between collector and the emitter. So my output will be 0 volt at that time. So this is how the output will be 0, friends. Okay. So this is how we have found out that, okay, whenever both the inputs are 1, the output is 0, and this is whenever any of the input is 0, output is 1. So this is NAND gate, you can say. Okay, so this basic gate which we have discussed, okay, is NAND gate. Okay, so whenever both the inputs are 1, the output is 0, otherwise the output is 1. So this is DTL basic NAND logic. Okay, I have explained it. So this is what I have discussed, that has been written in form. Okay, so all this we have discussed. Okay, what are the advantage? It has, comparative to RTL, it has good fan out, but not that much, and it is economical. It has having limited operating speed. That means they are not fast. Poor noise immunity. Okay, noise tolerance capacity is less for this DTL. Propagation delays are higher, that's why the speed is less. Okay, so these are the disadvantages, friends. RTL, DTLs, they are obsolete. Okay, TTL and CMOS are used nowadays for the ICs. Okay, so we will see the TTL and CMOS. So now we will go for the TTL. So it is very important logic family. It is transistor logic. TTL, transistor logic. Okay, and it is having the IC series 74XX54XX. So instead of this XX, we will have that IC number like 54017486. That's way, and it works with the power supply plus 5 volt. Okay, so that is one limitation that we will discuss. It has to work with the plus 5 volt. Okay, but it is having another good advantages that we will see in the advantages disadvantages section. But before going to that, let us try to understand this thing. Let's say this is the different transistor I am showing right now. Okay, so this transistor is containing two emitter terminals, and this is your base. Okay, so there are two emitter, and each emitter we will utilize as an input of the logic gate. So as you can see over here, it's equivalent circuit. I can draw like this. Base emitter junction is there, so this is behaving as one diode base emitter junction 1, and base emitter junction 2, it is behaving as another diode, because this will be your base, that is your P. Right now the it is NPN transistor, so it will be N over here in the emitter, so there will be two emitters. So this will be N, this will be N, but this base is P. So we can represent that emitter base junction as a PN junction diode like this. And on the collector side, we will be say it is another diode. So we can draw equivalent circuit to understand, just to understand that it will be containing two diodes in the emitter base junction. There are two emitters, so that we are considering two emitters. Another from the base collector junction, we will write, or we can draw another diode D3. Now, as friends, we have discussed in the DTL, same way over here. When this D1 will be on, whenever we are, let's say if I am applying high voltage on the base, so if I have to apply low voltage on this emitter 1, then this D1 will be forward bias. If I'm applying high voltage on the base, I'm applying low voltage on the emitter too, then this D2 will be on. Same way, this D3, whenever I'm having high voltage on the base, I'm applying low voltage on the collector, then this D3 will be on. Okay, so we will see how we can make the logic gate using TTL. So again, there is a example of the NAND gate, TTL NAND gate over here, and this configuration is totem pole, totem pole TTL. Now you may be wondering, this is totem pole TTL, but what is totem pole? So this arrangement of two transistor in between, there is a diode, okay, that is called totem pole output state. There are various you can say arrangements in the TTL, but we don't have to discuss that. Just this is very popular and advantageous, so just we will take this arrangement and I will explain you about the TTL NAND gate. Okay, now in this TTL NAND gate, whatever we have discussed in the previous slide, same way over here, there is multiple emitter transistor which is used as a Q1. This is my another transistor Q2. Okay, this is Q3 and this is Q4. Okay, now this Q1 can be represented like this as we have discussed earlier. So equivalent circuit of Q1 is drawn over here, and that Q1 is also connected with the Q2. All over here you can see this R1 resistor, R2 resistor, R3, they are connected with the power supply of VCC, which is plus 5 volt. Okay, so this is plus 5 volt of the VCC supply. Okay friends, now let us start discussing. Wait a minute. Okay, now let us start discussing this combination. So let's say in NAND gate, first of all, let us take A equals to 0, B equals to 0. So A and B both are grounded, as you can see in the first combination. Both the A and B are grounded. So from this point, the VCC is applied on the base of this transistor, which was Q1. Okay. So this diode D1 will be on, same way D2 will be on. If they are on, all the VCC will be gone through this path or this path. Okay, so what will happen to this diode D3? D3 will be in off state. Okay, so if D3 is off state, there is no voltage applied on the input of the Q2. There is no voltage applied on the input of the Q2. So 0 volt is applied on the Q2. So Q2 will be in off condition. So off condition matlab there is an open circuit between this 2 point of the collector and emitter. So this is open circuit. So there will not be any current which is flowing through this path. So again this Q4 का input भी 0 हो जाएगा because there is no current coming, because there is open circuit in between. Okay, so what will happen to this VCC? All this VCC which will be applied on the Vx. Okay, so this VCC is applied on that Q3 transistor. So Q3 पे VCC लगा, so Q3 will be on. So Q3 is on. That means there is a short between collector and emitter over here. So all this VCC will be having this on condition, so will be flowing. This diode D will be on because the VCC is coming. But over here Q4 is off because there is 0 volt is applied. So there is an open circuit over here. So again there is no path to go current from here to ground. Okay, so that will be applied in the output. So the output will be VCC high. Okay, so whenever this D1 and D2 both are 0 0, what will happen? Once again I am explaining. Okay, Q2 will be off because this is grounded, so no voltage is applied on the Q2. So Q2 is off. If Q2 is off, there is no current flowing through this R4 or there is no voltage drop. So again there is 0 applied, so Q4 will be off. Okay, but there is VCC applied on the this base, so that will be Q3 that will be on. If Q3 is on, all this VCC will be reaching to the output and you will have the output which is high. So first combination, whenever A is 0, B is 0, my output will be 1. So in NAND gate, whenever A is 0, B is 0, we have the output 1. Same way, let us look for another combination. Let's say A is 1 but B is 0. So A is 1, that means let's say we are applying plus VCC over here, and B is 0, that means VCC will be grounded. Now these two are in parallel. Okay, So all these VCC will be grounded. Okay, so again D3 will be off. So Q2 will be off because there is no voltage applied on the input of the Q2. Okay, so Q2 will be off. So this is open circuited again, as I explained earlier. So there is no current flowing, so there is no drop across the resistor R4. So again Q4 is off. But this VCC applied to the Q3. So Q3 will be on. So VCC will be going through this path. Diode D will be on, and the output will be 1 in this case. Same way, if I explain you about A equals to 0, okay, and B equals to 1, same way I can apply this logic for A is equals to 0, B equals to 1. In that case, A equals to 0, B equals to 1, this A is 0, so this diode D1 will be on, but B is 1, so D2 will be off. But all this VCC will be grounded through A, so again D3 will be off, so Q2 will be off, Q4 will be off, Q3 will be on, so the output will be reaching to this, will be Y is equals to 1. In this combination also, my output Y will be 1. Okay, now let us go for the last combination, which is when A and B both are 1. So as we can see in this combination, okay, A and B both are connected to VCC. So D1 will be off, it will not be flowing any current. Same way D2 will be off. So now there is one path for that VCC that will be going through D3. So the voltage high is applied over here on the transistor Q2. So Q2 is on. So there will be short circuit between collector and emitter of the Q2. So the current again from here it will flow, and there will be high voltage drop across the R4. So that will make your high voltage on the applied on the Q4. Transistor Q4 will be on. Q4 on, that means between collector and emitter there is a short circuit. Okay, short circuit over here. So now what will happen? Q3 that will not be getting VCC because all this VCC is going here. Okay, so Q3 is applied with the 0 volt. Okay, so that will be off. So there is an open circuit over here. D also, this is open. Okay, but this is sorted. So what you will get if you measure between this point and this point, you will get the low voltage near to the 0. So you will get 0 volt. That means your output is low. So whenever A is 1, B is 1, my output will be 0. So this is transistor logic where you have 4 transistors are used, Q1, Q2, Q3, Q4. Okay, this is totem pole arrangement. So there is one diode which is used. This is the equivalent circuit of Q1. Okay, so there is 4 transistors. This one, this one, this one, and Q4. Okay, so advantages: it is having low propagation delay, so they are fast. It is having high current sinking and sourcing. What is current sinking and sourcing? The ability to provide the current from the logic gate, and ability to this is providing current, that is called sourcing, and to sink the current, ability to absorb the current, that is called sinking. Okay, so this is like if it is going inside to this pin, then it is called sink, current sinking. Okay, so it is having good current sinking and good current sourcing capabilities, but it is having power dissipation high because it works on the 5 volt. Okay, so power dissipation is high. Okay, it is having less fan out compared to the CMOS, but it is quite better than RTL and DTL. But CMOS से कम है, CMOS में बहुत ज़्यादा fan out है, so that CMOS is quite better. This is having less noise immunity. Okay, less noise immunity. So it is having so performance, but TTL and CMOS both are used in the ICs. Okay, so this is about the TTL. Next, we will discuss about the CMOS, but right now I have to explain you first about FET, then I can discuss CMOS. So right now what I'm doing is just I will be jumping to the advantage, disadvantage of the CMOS, and then we will compare them, and I will cover the CMOS, this inverter circuit after the FET. Okay, so we will revisit this topic again after that FET chapter. Okay, but let us discuss the advantages, disadvantages. Okay, so in TTL we have seen it is requiring plus 5 volt, but in CMOS you require less compared to 5. Let's say it's working on 3.3 volt and lesser than that. It is having very high fan out. Let's say around 50, you can have the fan out value. Okay, noise margin is also good, but propagation delays are longer than the TTL, so they are not fast as TTL. All other things are good, but it is having less speed. That's it. Okay, power consumption is very good advantage. Good fan out, high noise margin. So that's why CMOS are largely used. So these are the advantages, disadvantages of the CMOS. Now let us compare this. In GTU, there will be question based on comparison so many times. Okay, so compare this logic family. So whatever we have discussed, TTL, CMOS today, RTL we have discussed in the previous lecture, DTL we have discussed today. So they are made up of which components? That already we know that they are transistors. TTL, they are made up of transistor, diodes, and resistor. CMOS, they are made up of MOSFET. Right now, I will not explain you, but I'll explain you what is MOSFET, what is FET. Okay, RTL, they are made up of resistors and transistor. DTL, they are made up of resistors, transistors, and diode. Okay, fan out of TTL is moderate. CMOS is having highest fan out. RTL and DTL, they don't have good fan out, but comparatively, DTL is having good fan out compared to the RTL. Now, this is very important. Propagation delay. Propagation delay of TTL is very good. Okay, so it is 10 nanosecond, 70 nanoseconds in the CMOS, 30 nanoseconds in the DTL, and this is 12 nanosecond in the RTL. Noise margin. Noise margin of the TTL is moderate, but CMOS is having very good noise margin. Okay, this RTL and DTL has low or poor noise margin. Power dissipation. As I've explained you, in CMOS you require very less power. Okay, so that is zero point 0.1 millivolt, which is very good. In all these, you can see it is around 10 millivolt to 30 millivolt. TTL is having 10 millivolt. RTL is having very high power dissipation. DTL is having comparatively low. So if you multiply this propagation delay and the power dissipation, we have discussed one parameter which is called speed power product. So it is speed power product is nothing but the power dissipation multiplied the propagation delay. So this is in joules. Okay, so it is very good in case of the CMOS, as you can see, zero point 0.7 picojoule. This is 100 picojoule, 144 picojoule, 130 picojoule. Okay, so this is very good in case of the CMOS, slightly better compared to RTL and DTL and TTL. Okay, circuitry, CMOS is little bit complex. TTL is also moderately complex. Over here it is written complex, but it is not that much complex, or you can say CMOS. Okay, these are not complex as we know. Basic logic gates of of TTL, that is a NAND gate. Uh, Over here it can be in CMOS NAND or not. Over here in RTL it is NOR, we have discussed. In DTL we have discussed it is NAND gate. Okay, now applications, as we know that they RTL, DTL are not used. TTLs are used in laboratory, and CMOS are largely used. So friend, this is about that chapter of the logic gates and logic family. So we are ending this chapter over here, and we will see about the CMOS, you can say basic logic gates explanation of the CMOS after the chapters of the FET. Okay, thank you for the listening.